nomenclature problem, you will not necessarily get a number 8 problem, but something similar, and you'll definitely get something like number 9. So number 9. We still have 82.66% carbon and 17.34% hydrogen. And it's asking us to find the empirical formula. Okay. Empirical formula. Okay. So now, because this 100%, because these 2% add up to be 100%, we can just straight up write down these numbers as grams of carbon, and then as grams of carbon, and then grams of hydrogen here. So 17.34 grams of hydrogen. Okay, so there's my two little numbers. Excuse me. So sorry, excuse me. Anyway. Okay, so now we have these both numbers. In order to do anything about empirical formulas, we have to turn any grams that we have into moles. I'll start off with hydrogen. So you got to go from grams of hydrogen to moles of hydrogen. So how do we go from grams to moles? We do the molar mass. We'll get a number. Right. Same thing for carbon. In 1 mole of carbon, there's 12.01 grams of carbon. Right? We're going to get an answer here. The answer for carbon is 6.88 moles of carbon. And then for hydrogen, it's 17.2 moles of hydrogen. Okay? So now that we're in moles, now we can actually do the cool stuff. So now when you're looking for empirical formula, you divide everything by the number that's smallest of all of them. In this case, it's the moles of carbon. This becomes a 1, right? That's just 6.88 divided by 6.88. This becomes a 2.5. And so now, this is the empirical formula we have so far. But that's not right because you cannot have decimals. So how do you get rid of that decimal? You multiply this by 2 because you get 2.5 times 2. That'll be what? 4, so 5 by 2, right? This is the improper fraction, or sorry, this is the fraction. You multiply this by 2, you just cancel out, get a 5, right? So C, but whatever you do to one element, you do to the other one. So C also gets doubled, and then hydrogen gets doubled. And so the answer here is C2H5. Sorry guys, technical issues here. Okay. So sorry, okay. So yeah, so this is a pretty standard problem you're going to see in the exam. And in case there are, so this guy only has 2 elements, there could be 3 elements. You just do the exact same thing, one more, and you divide by the smallest one, and you get, another element here, and you just make sure there's no decimals, and that's it. Okay. Sorry for that little pause there. Or you can skip it. It was like about a minute or 30 seconds, I don't know. Okay. Next one. We'll come back to number 10. You're going to see one, but I do kind of want to get you another one. Anyway, so we're going to go to 11. So H2 plus O2 H2O. As we see, so what mass is generated when 15 grams of oxygen? This is a typical stoichiometry problem. This is currently unbalanced. You see, there's more oxygen on this side than there are on this side. So that's no worries. So we're gonna balance everything independently. So far we have on this side we have 2 H's and 2 H's. See, so that's balanced. Great. This side though we have 2 oxygens. This side we'll have 1. How do you get from 1 to 2? You multiply this by 2. So this whole thing has to multiply by 2. But now that changes things, right? Now this side has 4. This side has 2. So how do you get from 2 to 4? You multiply this by 2. So this has to be 2. Right? I hope that kind of makes a little sense. So now the actual equation is 2 hydrogen gas plus just a regular old 1 oxygen gas gives us 2 H2O gases. Yeah? Cool. Now from here, this is where we can take it. We can take this now, and this has the proper moles for our mole ratio. So we're actually going to do stoichiometry. Let's ask us, okay, we have 15 grams of O2. How much water, we have 15 grams of O2, how much water can we make? So, okay, so this is a prime example of going from grams of reactant to moles of reactant to moles of product, and then from moles of product to grams of product, right? This thing, right? Grams of reactant, moles of reactant, moles of product, to then grams of product. Right. We've seen that before. This is something I really want you to know. And this is exactly what this is going to test you on. So here you're going to go from grams of oxygen. And now how do you go from grams of reactant to moles of reactant, the molar mass? In this case, oxygen is 32 grams of oxygen and 1 mole of oxygen. Okay, now we're in moles of reactant. How do you go from moles of reactant to moles of product? We look at the mole ratio. So in 1 mole of oxygen, right, this is invisible 1 here, there's 2 moles of water. Right. And just by looking at these coefficients there, we get that. Then, and this is why balancing the equation is so important. And now, how do you go from moles of a product to grams of a product? The molar mass. So in 1 mole of H2O, it should be about 18.0. Let's go 18. It should be about 18 grams of H2O. And at the end of it all, you're going to get an answer 16.9 grams of H2O. So let that kind of go in. So 2 steps. Balance the equation, and once you get it all balanced, then you bring it up to here to actually solve your stoichiometry problem. Cool. That's number 11. We're going to see if we can go all the way to number 15 for the first part, and then do the remaining for part 2. Okay, number 12. This is an important one because I got confused in class as well. So you have 15 grams. I don't like that 15. You know what? Let's change color. Let's be a little rebellious today. You have 15 grams of sulfuric acid, and you have to know what sulfuric acid looks like. It's H2SO4. 15 grams of sulfuric acid mixed with 20.0 grams of potassium hydroxide. Right? This is where you'd be testing a nomenclature. You'd be testing a nomenclature without really knowing it. You know what I mean? So yeah. So make sure you know how to do that. A really quick recap. Acid nomenclature. When you have a polyatomic thing here like that, polyatomics, if they end in ATE, they're always going to end in ic acid. If your polyatomic ends in ITE, they're always going to end in os acid. Right? In this case, it asks for sulfuric acid. Sulfuric, well, we have sulfate, right? Sulfate ends with an ATE. So example, sulfate. Nah, it's a little messy. Anyway, that's fine. We have sulfate. That ATE then has to become an sulfuric acid, right? Sulfuric acid. And then anytime you see something like this, like HX with X is like a halogen, it should be called hydrochloric or hydro whatever. Hydrochloric acid. So this is HCl. But notice how this hydro part is always going to remain the same. This is the base of your whatever that X is. So chloric, bromic, iotic, and always ends in acid, an ic acid. So hydrochloric acid. Okay. Give you a second to look at that. And now we erase. Okay, now. So this is how I've identified what stuff is. But it's asking us to find a limiting reactant. The only way to do this is by having a mole ratio. And the only way you get mole ratios is to form an equation. So we have to form an equation. So it says what happens when you react sulfuric acid in aqueous plus KOH in aqueous. Okay, fair enough. Okay. So, what always this is an acid, that's a base. I hope you guys know the acid base, right? Acid base, acid base, acid base. Whenever you have an acid base reaction, one of the products will always be water. No matter what, always be water. And the next thing is you have to pretend this is a double displacement, right? So this H is going to replace this K, and this S is going to, well, that's it. To get a double displacement, that's what you're going to need. That H is going to replace that K. So in this case, we get HOH, right, plus KSO4. What is these HOH? That's just water, right, which I've already accounted for. This thing, though, now needs to be there. So in fact, it's going to be K2SO4. And that 2 comes from the fact that sulfuric acid is a 2-, right? Do keep in mind that's a 2-, so it's going to distribute its little stuff here when it actually combines with the K. And you can still see the same effect there. So the whole equation is actually going to be H2SO4 aqueous. Make sure you know the state symbols. Right? It's this thing here. So now, once you have figured that out, you can now actually start doing math. And so it's very important that you know that you will always form water if you have an acid and base, and then it's basically a double displacement. So for the next guy, this guy, it's just replacing the cation with the anion. I'm going to erase that right now, but just let you look at that. Okay. Oh, I shouldn't erase the top one. So that's our equation. Now we have to make sure everything is balanced. So everything may be balanced. I don't know though. We don't know. On this side, we have 2 potassiums, 1 potassium. Oh, not balanced. How do you go from 1 to 2? Multiply this by 2. So this has to have a 2 in front of it now. Let's change to it. This has to have a 2 in front of it now. Okay, but that also means that we're going to have to increase the amount of O and H in the whole system. So sulfuric acid, let's go with that first. So if you see a polyatomic, when you balance it, you can think of it like a group itself. So in this case, we have 1 sulfite, or 1 sulfate, my bad. Over here, we have 1 sulfate. Okay, good. That's balanced. Okay, so now comes the water. On this side, we have 2 hydrogens plus 2 more hydrogens. Right, and that comes from the 2 here. So there's 2 here, and then there's 2 there. How many on this side? We have 2 hydrogens. Okay, how do you go from 4 to 2? You multiply this side by 2, so you just add a 2 there. Okay, cool, sick. Let's check the number of oxygens now. Only including these oxygens, because these have already been accounted for. You just include this, there's 2 oxygens. This side, 2 oxygens. Bam, everything is now balanced. So you had to add a 2 in front of here and 2 in front of there. Okay, I'm telling you guys, a lot of work. So make sure you guys understand that this is how you do a balanced equation. Okay, let me erase this. Okay, so now we have everything balanced. Now we can decide what's the limiting reactor. So how your professor does this is kind of confusing. So I'm going to teach you the way that you guys have been taught by Alex and how basically I was taught, so how everyone was taught. And how we do that is you give us the 2 grams of stuff that we have. Right, or 15 grams of sulfuric acid or 20 grams of KOH. And we just assume, or sorry, we don't assume, but we're like, okay, we go to the products. We pick a product. At this point, any product would be fine because it's not asking you to find a product. It's just asking you to see which one's limiting. So I would pick water, right? It's the easy one. I would pick water because it's the lowest in molar mass. I don't want to calculate too much. You can't also pick this, you just now have to calculate a larger molar mass. But regardless, we want to pick this. Arbitrary. And then all we do is go from grams of our reactant to grams of product, like we did last time. Alright, so let me show you an example. So in this case, we have sulfuric acid. The molar mass, how do we go from grams to moles? Well, we have to do the molar mass, 9 grams and 1 mole of sulfuric acid. Right? How do you go from moles of a reactant to moles of a product? The mole ratio. So there is 1 mole of sulfuric acid for 2 moles of water. And then in 1 mole of water, you have 18 grams of water. Actually, you know what, guys? Yes, you can go all the way to grams. Go for it. But for this case, it doesn't ask us to find anything here. So you can even just do it. You can stop here if you want, just to make it easier for yourself in terms of calculations. All you need is the moles. That'll be fine. You can go grams. Grams will get you the answer too, but that's just extra work. And now we do the exact same thing for this guy. I'm not going to explain anything. I'm going to keep going ahead. Now we look for KOH. There's 2 moles of KOH for every 2 moles of water. So that's different, right? And you're going to get an answer. Let me quickly calculate these because these are not on your practice exam. Okay. 0.306 moles of water. Okay. And this one's going to be 20 times 2. Divide that by 56.11 times 2. 0.356 moles. Okay. And so we see immediately off the bat, when we do this and we pick an arbitrary one, we see that indeed the one that makes the least amount of water is sulfuric acid at about 0.306, as opposed to KOH is at 0.356. And so the answer to this one is not asking a numerical answer, it's asking which one's the limiting reactant. So clearly we just look at which one has least. And so the answer is A, sulfuric acid. That is a limiting reactant. Cool? Okay, we're going to stop the video and continue this on part 2.